Hello, let's get a quick review on natural transformation before we look into many alternatives way to talk about them. And I will take this time the classical definition. So if you already know AOD and the like, this is just brushing up again. So let's start with two categories, C and D, and two functors, F and G. So that's a drawing in cat, the category whose objects are categories and arrows are functors, and now we're trying to define what it means to have an arrow between those two arrows, F and G. So how could we define alpha? Well, let's unpack the definition just a bit to make sure we're on the same page. So category C has objects, here X, Y, Z, U, and it also has morphisms, F, G, H, and it has special morphisms named IDX, or identity on each objects. It also has a composition, and this identity is a left and right identity for the composition. This composition, moreover, is associative. So all those axioms really justify this graphical notation in a way, because it says, there's nothing more than what you see here in this string FGH. You can do what you want, but you won't get anything more by rearranging the way you compute those things. And a functor maps objects from C to objects in D, another category. And it also maps these arrows, F, G, H. And so the identity of X will be mapped to F of the identity of X. But D is also a category, so it also has a category, an arrow ID F of X. So what we will require from this mapping F will be that F of the identity of X is equal to the identity of F of X. And moreover, when we compose in C, G and F, and we transport this arrow, it will be equal to transporting the arrows F and G and then composing them together in D. So that's an important point, that those composition G compose F and F of G compose F of F are not in the same category. They have nothing to do with each other. They might be completely different. But those two axioms with the category axiom allow us to say you can compose any string you want. You can express this string that has been drawn the way you want. It's all going to be equal. So those axioms really justify, again, this graphical calculus where we transport something in C into something in D. And there are many more equalities you can write. So those were categories and functors. Now let's go on to natural transformation. So in that context, let's imagine we have the same two functors F and G, and we're trying to relate somehow F and G. So we might as well be able to relate the action of F and G on the objects. So we give ourselves a family of morphisms in D, indexed by the objects in C. So alpha X is a morphism in D, although it's indexed by the objects of C that lives in D world. And once we have that, we have a slight problem, because we have two ways to travel from F of X to G of Y, and we would want to map everything in a uniform way. So we require to have those two ways to travel from F of X to G of Y by means, in a way, of little f in C and this added structure that we gave ourselves, those alpha. So we want those two ways to be equal, and this will simplify our life, of course, because now not only have we associated to each object X some morphism alpha X in D, but we also have a way to associate to each f some morphism alpha f in D, and which is defined whichever way you want by going from above or from below in this diagram.